Hi, and welcome to the first of 3 videos from the mechanics section from the Year 2 part of the course, where we're going to be having a look at vectors in kinematics. And essentially what we're going to be doing is rehashing our Year 1 work that we did on SUVAT and variable acceleration, but putting it in the context of vectors. And we'll also have a look in the next video at how we can do vectors with projectiles as well. So here we go. First video, we're just going to be looking at using vectors to describe two-dimensional motion, whereas in Year 1 it was just one-dimensional, and looking at SUVAT equations with vectors. Okay, so let's just have a quick recap of what we did in Year 1. So we've got a SUVAT question here with motion in a straight line. So there we go, that's the information from the question. We've got a particle moving on a straight line, and we're measuring its displacement from the point O, and the red information there is the information in the question. And part A is asking us for the maximum velocity, the maximum displacement from O. So P is going to move, and it's going to come to a point where it's going to stop because we've got acceleration is negative, and that's going to be the point when it's furthest away from O. So let's have a look at all the SUVAT stuff that we've got. So S is the thing we're trying to find, U is 3, V is 0, A is minus 1.2, and we don't know T, we don't need it. So here we go, V squared equals U squared plus 2AS. Bash all the numbers into there. Do a bit of solving, and we know that our maximum displacement initially is going to be 3.75 meters. Okay, on we go to part B, and what happens is P is going to move back in that direction now. So displacement and velocity when T is 8. So there we go again. So here comes our displacement, S equals U plus UT plus half AT squared. So we're now 14.4 meters away from O, but obviously displacement, it's got direction, so it's minus 14.4 meters. And our velocity at that point in time is minus 6.6 meters per second, and this thing will just keep on accelerating and accelerating in the direction off to the left. So what we've got there is basically what's happening is we've got directions on our positive and negative displacement, velocity, acceleration, so they are technically vectors, but the motion is only occurring in one direction, that horizontal direction. It's just moving in a straight line, so it's just going kind of backwards and forwards in that direction. And so what we're going to be looking at in this video is what happens if P moves in more than one direction. So let's say it does something like that. So we've got to be able to deal with that. Okay, so that's what we're going for. So let's have a look. Our particle P is going to move with horizontal and vertical components. So now let's imagine it starts from a point with a position vector, we're going to call that R0, and that's going to be relative to some fixed origin, and it moves with velocity t. So what we've got is our fixed origin, some points here that we're going to measure everything against, same as we had in our previous example. We've got a starting point, I'm going to call it R0, and P is just going to move in this direction, and the direction is given in the velocity. And so what happens is, after P moves, it is now, let's say, at a point there, and so in order to get the displacement from O, we've got to go O to there, and then from there to there. So essentially we're adding together two vectors. So what we get is that, because this vector here is simply this is in meters per second, so we just tell how far has it moved in each second, and that's our VT there. So our new position is going to be R equals R0 plus VT. So there's that extra little bit of a thing to think about when we're dealing with vectors. So let's have a look. We've got an example here. Particle moves with velocity minus 2i plus 7j kilometers per hour. We've got an initial position 4i minus 8j, and we've got to find the position vector of the particle 3 hours later, and then for part B, the distance when it's northeast of our origin. So here we go for part A. So again, I always like a diagram to get my head around what's going on. So that's what's going on there. So when t equals 3, we've got our equation there, r equals r0 plus v times t. So let's just plug t equals 3 into there with the relevant information that we've got. And clearly there's our position vector, r is minus 2i plus 13j. Okay, reasonably straightforward. Let's now have a look at the second part of the question. The distance p is from O when it's northeast of the origin. So what we've got is our point P is there, and when it's northeast, we know that the horizontal and the vertical components are going to be the same. So that's our way into this question. So what we need to do is say, well, if we've got our displacement vector, which is that, so that's r equals r naught plus vt, and we need to find the time at which it's northeast. What I'm going to do is just do a little bit of rearranging here. So I'm going to get kind of the I components all together and the j components all together. So for the I components, I've got 4i coming from there, and I've got minus 2 times t coming from there. So that's that one. And then for the j components, I've got minus 8 there, plus 7t coming from here. So we've got that. The advantage of doing that is because now we can say, well, when are the two things the same, i.e. when it's northeast, so we can create that equation there. And now what we've got is an equation we can just solve in terms of t, do the solving, and we've got t equals 4/3. So we know that our particle is directly northeast of our original start, our original origin, after 4/3 hours. And so all we need now, we're being asked for the distance. So we've got to work out, first of all, what our location is. So we'll go for that. Put in the 4/3. To be fair, we don't need to do it with both bits because we know they're the same. But that gives us that vector there. And just worth mentioning, this is complete coincidence, the fact that I've got t equals 4/3 and these values here are 4/3. Let's say complete coincidence. So don't think that's going to happen every single time. And because we're after the distance, we're going to need to do a bit of Pythagoras. There we go. And so our distance is 1.89 kilometers. Okay, moving on. Let's put this into context, do a bit of problem solving. So we've got a hockey player here taking a long corner and strikes the ball, and it's got initial velocity, and we've got its velocity after 1.2 seconds. And so what we've got to do is answer our questions here, bearing in mind the other piece of information, the corner is taking position 5 meters in from the corner on the baseline, because that's where you take a long corner from in hockey. So firstly, find the acceleration of the ball. So here we go with our SUVAT. Now it's kind of, we tend to use r as displacement instead of s, so kind of RUVAT if you want. Let's put in all the information that we know. There's u, there's v, the acceleration we don't know, and we do know t. So we're going to be using v equals u plus at to find our acceleration. There we go. So put in the values, and now we've just got to rearrange for a as normal. So we're going to move 3.6i and 3.2j over to the other side. There they go. And now do the divide. And there we go. We've got acceleration in terms of the two components. Minus 0.75i minus 0.3 recurring, or 1/3 j. Right. That's first bit. So now we've got to find an expression for r in terms of t. So what we'll do, we're going to say, we're going to call rb is going to be the displacement of the ball. So rb is the thing we're looking for. Here's the information that we had previously. There's the acceleration that we had from the last question, and t we don't know. So, but we're going to use t in this equation, so let's use displacement is ut plus half at squared. And in it all goes, so we've got 3.6i plus 3.2j times t, and there's the half at squared. But we're not quite done there, because we've got to remember that our short corner was taken from 5 meters in from the corner flag, from the corner of the pitch, and that's our origin. So we've got to add on our adjustments for the fact that we're 5 meters in from the corner of the pitch. The other thing to mention is that in the previous example, we used r equals r0 plus vt, and that we used that one because in that particular context, the acceleration was 0. We're not using it now because we've got acceleration, so we haven't got constant velocity, which is why we've used r equals ut plus half at squared. Right, so what we'll do is just do a little bit of tidying up there. So now what I've got is, I've just included my 5i from the air. I've just included it in the I components here. So I've rearranged, got my I components, and then got my j components. Right, so there's the expression for the displacement of the ball at time t. So on we go to the next part of the question. It says, given that a teammate runs such as position r equals 3 plus 4ti plus 2.9tj relative to 0 at time t, does the teammate receive the ball? So is the pass going to get to her? So here we go. If we say, let's call rt, we had rb, which was our displacement for our ball. Let's go for rt being the displacement of our teammate. So we've got rt equals 3 plus 4ti plus 2.9tj. And if she receives the ball, then those two things are going to be the same for some value of t. So let's put our two expressions equal to each other. There we go. And now try and see if we can find some value of t that will work for both components. So there's our expression, and let's initially work with the vertical component. It doesn't really matter. I've chosen the vertical one because it appears to be a little bit more simple. I don't know if it is or not, but there we go. That's what we've got. So 3.2t minus 0.16 recurring t squared equals 2.9t. That's just the j component. Where's my mouse gone there? The j component from there equal to the j component from there for some value of t. Rearrange it, do a bit of solving. So we've got t equals 0 or t equals 1.8. And now we need to check those values of t against our I components. So t equals 0, we know that's not going to be 1, but let's just have a little look at it anyway. So when t equals 0, we've got I is for the ball, it's 5 metres in from the corner flag, which we already knew. For the player, our teammate, as it turns out, coming up to here, she's 3 metres in from the corner flag. And then let's have a look at what happens with t equals 1.8. The I components, so we've got to go put 1.8 into here, and that gives us a value of 10.265. And also for our teammate, so now what we've got to do is put our 1.8 into the I component for our teammate, which is this one over here, and that gives us a value of 10.2. Right, so what does that tell us? Well, our mechanics models are all models with the ball and teammates as particles, so clearly these two values are not the same. So therefore, the teammate doesn't receive the ball. Except, of course, in reality, these figures here tell us our teammate's only 6.5 centimetres away from the ball. So in actual fact, we can probably say, yes, she does actually receive the ball. And again, as long as you clearly justify which way round you're going to be explaining that one, then you would be okay with either response. So there we go.